Hello everyone and welcome to another video. So today I'd like to continue our exploration on how to effectively and efficiently design linear controllers. If you've been following our discussion so far, you know that we've covered a lot of different topics regarding linear control design, and I want to start off today by maybe quickly recapping some of these techniques because I think they're both critical prereqs to this discussion as well as they help motivate and frame the current discussion for today. So let's quickly just make a quick table here talking about the different analysis or concepts that we've covered, maybe in the first column. And then let's also look at what is the analytical tool that is needed for this concept. And then lastly, let's also think about what is the MATLAB tool that will help us implement this idea or understand it better. Okay, and then in the far side of the screen here, I'm going to pop up a couple of the relevant videos that we talked about that cover some of these discussions earlier. So let's start off with maybe the easiest one. So if you remember, we had a lot of discussion here on performance metrics like percent overshoot, settling time, rise time, etc. Right? And we saw that, okay, the analytical tool that helps us understand these concepts where you basically look at things like the step response. And we also saw that, you know what, you could also understand the percent overshoot and settling time for some systems, namely second order systems or second order dominant systems, by looking at regions of the complex plane. Basically, where do the poles land? And again, over here on the side are 3 of the YouTube videos that discuss these concepts and these tools here. And we saw that MATLAB actually provides different sets of tools to do this type of analysis. So there's things like the step function, the LSIM function. There's actually the linear system analyzer is another tool that allows us to do this. And many more here. So I just wanted to list a few of these, okay? So this was one concept that we saw was critical for designing control systems. What else did we see? We had a discussion actually on DC gain, right? And we saw that, all right, if you want to understand the DC gain of the system, what you're really thinking about is looking at the Bode plot, specifically at low frequencies. And MATLAB has a nice tool for this. It has a Bode function, right, which will allow us to do that. Okay, what other types of concepts did we cover? We also looked at system bandwidth. And we saw that, okay, if you want to look at bandwidth, again, you're looking at a Bode plot, but you're looking at a Bode plot of the closed loop system. Right? And again, the thing that's relevant here is the Bode function. While we're still talking about Bode plots, remember we also had a discussion here on gain and phase margin. Okay, and we saw that gain and phase margin, the idea was, again, you still look at a Bode plot, but now you're looking at a Bode plot of the loop transfer function, not the closed loop system, right? And again, you could use Bode, or also MATLAB has a margin tool for this. And again, as I discuss all these, I'm going to flash up the relevant videos over here on the other side of the board. So again, I will also leave descriptions to all of these videos leave URLs to all of these videos in the description of this video here. What else did we talk about while we were designing controllers? Oh, how about root locus? That turned out to be a very critical concept. And the ideas with root locus here were obviously you could, well, plot the root locus. That's kind of self-explanatory. But there were other tools like Routh-Hurwitz, which also allowed us to help understand this concept a little better here. And again, MATLAB had tools for this, like RLocus. Okay? So the reason I wanted to put up this list here is because, again, we've had a lot of good discussions so far talking about all of these different topics here, and I want to make sure that you've watched all these and understand these concepts because, again, we're going to make use of them here, and it really helps understand that if you look at this, it looks a little bit like, you can see it's a pretty healthy list of topics, but they require a somewhat scattered set of tools to deal with, right? You've got the linear system analyzer, you've got margin and Bode, and you have to do all these different types of analysis to see the whole picture, right? Because we saw all of these different concepts feed into designing a linear control system. So I bet you're thinking right now and wishing, gosh, wouldn't it be swell if there was just one tool that would allow me to do all of this analysis together at once? Well, I hope you live in Agrabah with your pet monkey Abu, because today I'm going to be your genie and make all of your dreams come true. We are going to introduce what's called the Control System Designer, which is a tool in MATLAB which is going to allow us to do all of these tasks and more. So it's going to allow us to do all kinds of things. Like, for example, it's going to allow us to view the root locus. It's going to allow us to manipulate the root locus. It's going to allow us to think about modifying a controller structure in real time. So I'll say modifying controller structure, and seeing the results / ramifications in real time. It's going to allow us to look at the time domain response of the system. It's going to allow us to look at the frequency domain response of the system. So it's all of these things put together in one tool that, if we understand how to use this effectively, it's going to really help our control system design workflows. So isn't this great? And you know what? You still have 2 wishes left. So if you'll chase them anywhere and you've got time to spare, then let me share this whole new world with you. Okay, so before we dive into MATLAB, I want to talk a little bit about just the workflow for using the Control System Designer. We're going to see that it's a little bit different. So it might behoove us to quickly discuss a relevant way to use this effectively. Just as a quick note, the Control System Designer, you may have heard this by other monikers in the past. I think when I was using this, or when I first learned about it, I learned about it as a CISO tool. So let's just make a quick note that it used to be called CISO. There was a thing called CISO tool. There was also a thing called RL tool. And I think these got renamed back in like MATLAB R2015A or something like that. And everything now that's newer is called the Control System Designer. So just FYI, if you hear people talking about CISO tool or RL tool, that's basically the same thing. So with that being said, the workflow for using the Control System Designer here, it's I think of it as a 7-step process. So the first thing that you're going to do here is you're going to generate a dynamic model of your system. Usually the plant. So things that are helpful is you could use things like the TF function, the ZPK function, etc., the state space function. All those things in MATLAB could help you generate just basically a dynamic system model of your plant that we can then load into the Control System Designer. So that's the second step. So step 2 here is go ahead and start the Control System Designer. And load in the plant model. That's the thing that we developed in step 1. All right, so again, the helpful command here is obviously it's going to be Control System Designer. And I apologize for my handwriting. This should be a capital S and a capital D and a lowercase c. Okay, so that will get the system started. We'll look at another way to get it started as well. And we'll also look at how to load in the plant. But once you have this all set up, what's really nice about the Control System Designer is you can add design requirements. Okay. So these are things like percent overshoot, you know, pole locations, frequency domain response, time domain response, all those different requirements can be all captured and codified in the one spot. Okay, the next few things is once you have that all set up, step 4 is now that you have your plant in there, you have your design requirements, you can basically try to go ahead and just design your controller or your compensator, however you want to look at it. Directly in the control system designer. And we're going to take a look at how to do that. Once you're happy with your controller that you've designed, we're going to have to export that compensator back to the main MATLAB workspace. So step 5, it's export your controller / compensator to MATLAB workspace. We're going to see what this means in a little bit. You might think everything is one giant workspace, but it's not really. Okay, then once you're done with that and you have it in the main MATLAB workspace, what I would do is I would save your controller and possibly save your session. And again, this will make a little bit more sense what we're talking about. What is your session once we get into it? So again, maybe the relevant functions in MATLAB that are helpful are obviously save at that point. Okay, and then the last thing that I would do is once you have all of this controller designed and saved, I would go ahead and make sure that I simulate my system to validate performance. Simulate system to validate performance. And in this case, I would basically think about building a Simulink model that represents this plant and this controller that I've designed and make sure that it actually performs the way that you expect it to. Okay, so let's think about using an example. I always like concrete examples. So with this workflow in mind, let's think about an example that we can use and see if this control system designer will help us in this scenario. So the scenario I want to look at here is our good old friend, the DC motor. So again, if you haven't had a chance, we have a video talking about how to derive the transfer function or a dynamic system model for a DC motor. If you don't care about that and all you want to do is just look at this as just some third order transfer function, that's great as well. But what I want to look at is how can we do DC motor position control. And in this case, we are just going to be using proportional control. We're going to have videos later that look at more complicated control architectures, but let's keep it simple when we're just introducing this tool, okay? So the way we want to think about this is if you remember the plant, let's call it GP of S. This is the motor position or the motor angle over the armature voltage or voltage applied to the DC motor. We said that this transfer function, you know, it's a bunch of constants, but at the end of the day, when you plug in numbers, here's some transfer function. You could think about this as just a system that is dropped into your lap if you want, right? Some other team in your job has gone ahead and said, here's the model of your plant. Go ahead and build me a controller that will deal with it. So here's what it looks like, 4845S. Okay? So again, in case this is hard to read in the denominator, SQ plus 1021 S squared plus 4845 S. This is just your transfer function, okay? So what we want to think about now is, okay, here's my system, GP of S, right? And you give it a control signal U, which is, in this case, the voltage to the motor, and it spits out the angle of the motor, of how far it's turned. And what we want to think about now is using our specific classical control architecture where all I want to do is design a controller C of S, where all this C of S is just a gain K. It's a constant gain. We're going to look at, again, we'll look at something more complicated a little bit later, but this is the game plan. The game plan is find a value of K that will make this thing behave desirably. So we now need to think about what does desirably mean. Let's assume that maybe your manager drops some performance requirements onto your lap along with this system here. So let's talk about performance requirements. Okay, so let's say that they say you gotta have less than 40% overshoot. That's the maximum they'll tolerate. You have to have a rise time of 1 second or better. You need a settling time of less than 3 seconds. And this is to within 2% of final value. That's our band for how much we consider it to be settled. Okay, you need a gain margin. Oops, gain margin of 20 dB or better, and a phase margin of 30 degrees or better. And then finally, the system better have a bandwidth of greater than 5 radians per second. So at this point, I guess hopefully it makes sense why I say you want to make sure you watch all of those other previous videos, because if you watch all the other previous videos, all of these requirements should make sense to you, right? You should understand physically what does the system have to do in order to meet all of these, or what should it behave like in order to meet all these. So our game plan now is design a controller K that will simultaneously meet all of these, right? And what we saw earlier is, sure, you've got the tool set that you could do this right now by hobbling together all of these different types of analysis, like loop transfer function Bode plots, closed loop transfer function Bode plots, root locus, pole locations, all of that kind of stuff. I'm sure you could do it, but I want to make the case for this control system designer is going to make this workflow a lot easier. So with that being said, let's jump over to MATLAB, get the control system designer fired up, build this transfer function, and basically walk through these 7 steps and see if we can use it to effectively and efficiently design that proportional controller K.
So here was our 7 steps. Let's just start with step 1, which is generating a dynamic model of the plant. So to do that, let's go over to MATLAB and go ahead and start ourselves a new script. I'm going to say we are using this to explore how to use the control system designer to create a proportional feedback controller. Okay, so we'll start with our normal clear CLC, close all, and maybe before we get started, let's go ahead and save this script. So Control S to save, and what I'm going to do is I'm going to put this someplace. I have a folder already, and whatever you do, do not call this Control System Designer, because that's the name of a function we're going to use to start the designer. So you can call it Control System Designer script or something like that if you really want to. Okay, now what we're going to do is let's just go ahead and start off with step 1, right? Generate plant model. Okay, so we're going to do this the same way we did earlier. We're just going to go ahead and create a numerator coefficient, a vector for the numerator coefficients. And then, oops, I should call that GP numerator. And then GP denominator is a vector of the coefficients of the denominator polynomial. So that was, I think, something like that. Great. And then the overall transfer function for our system is just going to be TF of num and then den. Great. So if we go ahead and run this, I'll change the folder to this current location. And here is our transfer function between the armature voltage and the position of the motor. Okay, so next, let's go on to, I believe we are on to now step 2, right? Step 2 was we need to start the control system designer and then load in the plant model. Okay, so hopping back to MATLAB, there's a couple of ways we can do this. Step 2, start the control system designer. So one of the ways you can do this is you come up here to the apps tab in your MATLAB window, and you come here, there's all these different apps. So I'm going to hit this little drop down here, and I'm going to look for the control system design and analysis. And you see here are all these different apps, and here's the one we're interested in, the control system designer. I can go ahead and star that actually because it's kind of helpful, so that will move that up here to my favorites. But one way you can do this is you can just click on this icon, And what it will do is it's going to start what's called the Control System Designer. And we'll give that a second to populate. And I'm going to show you actually a second way to get this as well. And it pops up for me on a different window. So let me go ahead and drag it over here. It's still initializing. You're seeing it's popping up a whole bunch of different plots. And here we go. This is the Control System Designer. Let me close this real quick, and I'll look at a different way to open it and just get to this exact same spot. So the other way you can do this, when you try to close this, you get this little save session notification. I'm going to hit no because I don't care about this for now. The other way you can do this is if you just go ahead and type help Control System Designer. You see that basically you could call it like a function. In fact, you can call it like a function and pass it in the plant model if you'd like. I'm not going to do that. Let's just go ahead and open the Control System Designer programmatically. And I'm going to say without loading in the plant model, because I want to do this manually just so we can get some experience. So I'm going to say Control System Designer, like that. And I guess you can call it with empty parentheses if you really want to or not. But now if we run this, when we hit line 16, it's going to initialize the Control System Designer. So here it goes. It's pulling up. And why don't I go ahead and maximize this just so we can get a better understanding of what's going on. So the Control System Designer, it looks like a lot initially, and it really is. It has a lot of function and features in here, but really at its heart, it's a root locus design tool where it's going to show you the root locus of a given architecture of a system, and it will also show you things like the step response of the system as well as frequency domain analysis of that system. So the question that's probably on your head is, what system are we talking about here? So to answer that and to finish up our step number 2, I'm going to come up here to this tab which says Control System, and you see there's a tab that says Edit Architecture. So you can click on either this drop down and then select Edit Architecture, or you can just click on this upper half of the button. Either way, what it's going to do is when you click on that, if you give it a second, here, this window will pop up, and it shows you all of the different architectures that are available for this system. So it's quite robust. There's a lot of different architectures and block diagrams that you can analyze. Let's go here with this one here at the very top, because if you look at this, this is the classical system that we're looking at. You have a plant G. You have a potential to add a compensator or a controller C. It also has a model for you allowing to model sensor dynamics, which are denoted here as H, as well as a pre-filter, which is denoted as F. So we're going to ignore F and H for our purposes and just focus on G and C. So the first thing I want to do is, you remember that back in our MATLAB workspace, we made this variable called GP, which was the transfer function of the system. I need to load that in as the plant model here. So in order to do that, I'm going to come over here and I see G, and I'm going to click on this import button. And when I click on the import button, it brings up this other dialog, which is going to allow you to look in the base workspace, which is the MATLAB workspace, for any available models like transfer functions, ZPKs, state spaces, things like that. So we only had one, so this is the only thing available. I'm going to click on it, and when I click on import, what that's going to do is that's going to jam that transfer function for our DC motor into this G block. So when I hit OK, watch, all of these plots in the back should update now. So now what we should see is this is the root locus for our system with that architecture we had earlier that we showed. Maybe I'll bring this back up so we can see with this particular architecture. Now, the next thing you're probably wondering is, what did MATLAB throw in here for F, C, and H? So to get that, you can come over to the left side of the Control System Designer, and you see it's got all of these listed here. So if I click on F, it actually tells you that, oh, it's just a static gain of value 1, which is perfect. We don't want a pre-filter in here. I want it to be like it's not even there, or it's a gain of 1. Same thing for H. If you look at H, it's just a value of 1. That's perfect. I don't have a sensor model in here. Now, how about C? C is also a gain of 1. So right now, what we have is, again, let me pull up this architecture diagram, is all of F, C, and H are all 1s. Now, the place where it makes a difference is G. If you click on this, look at this. It has now loaded in the G that we defined in the MATLAB workspace. So we're ready to start working. We've completed step 2, where we have gone ahead and imported the transfer function model for the plant into the control system designer, and we've set the architecture to be the classical inner loop, single loop feedback control system that we want. So let's go ahead and think about moving on to the next step. All right, so moving on to step number 3, that was where we were going to add design requirements. Now, before we think about adding them, let's review what were the design requirements. So if you remember, we said there had to be less than 40% overshoot, a rise time of less than 1 second, settling time to within 2% of 3 seconds or better. We have more than 20 decibels of gain margin and 30 degrees of phase margin, and we wanted the system to have a bandwidth of greater than 5 radians per second. Now, these are the requirements. Maybe what we should think about is translating these into what types of plots or analysis do we need to do or view so that we can verify that these requirements are met. So the first 3, I think you will all agree that if we look at the step response of the system, we should be able to understand all those things like percent overshoot, rise time, settling time, all that kind of good stuff. Also, we could look at trying to understand where the poles need to be in the complex plane. So we could look at the root locus of the system to try to tease out those percent overshoot and those other types of performance metrics. Notice that there's an asterisk there, and I feel like it's my duty to remind you that the root locus is actually, it's only accurate and precise for second order systems or systems which are second order dominant. If you have higher order dynamics, the root locus, although we might be able to sketch areas of the complex plane where poles should fall, it's not going to be 100% foolproof. And we'll look at an example of that actually in one of our future videos. So really, the step response is the surefire way to make sure that you satisfy the percent overshoot, rise time, and settling time. The root locus is a nice to have, and we'll look at it, but I just want to make sure we're all on the same page that it's maybe a starting point or a suggestion, and it's really the step response is what you want to look at. Okay, let's move on to the gain margin and phase margin. How are we going to analyze that? Well, if you remember, what we need to do then is make a Bode plot of the loop transfer function or the loop gain, right? So in this case, it would just be the transfer function G times C. For bandwidth, that's another story. Bandwidth, we actually want the Bode plot of the closed loop system from the reference input to the actual output. So these are all of the different types of plots that we're going to need to make, and we're going to see that the control system designer can handle all of these. So with that being said, let's go ahead and pop back over to the control system designer and think about adding these. So we see that by default, we've actually got almost everything we need. We've got the root locus up here in the upper right. We've got a step response, and if you look at this very closely, it says R2Y. And again, if we come here to the architecture diagram, you'll see that this is indeed the closed loop step response from the reference input to the output, right? So down here is where we're going to want to be looking at performance metrics like percent overshoot and things like that. Finally, we also have a Bode plot of the loop transfer function. So great, this plot will be very useful for understanding gain and phase margin. Now, we need to add a couple of things. So one of the plots that are missing from our list is we need the closed loop transfer function Bode plot from R to Y. So in order to do that, so we can get bandwidth, I'm going to come up here to the control system tab, and you see this thing that says new plot? Let's click on new plot. There's a whole bunch of different plots you can put. Let's say I want a new Bode, and again, we see our nice diagram, and now I want the Bode plot from R to Y, right? The entire closed loop Bode plot. So if I click on this little drop down, I can pick the transfer function here, IO transfer, R to Y. That's exactly what I'm looking for. If I hit plot, now what we're going to see is another Bode plot that shows up, which is now the closed loop Bode plot. And this might be helpful if we grab and drag, and I'm going to show you can actually pull this apart and you kind of rearrange as appropriate. So here we go. This looks awesome. So now I think we've got all of the plots we're looking for. I do want to add one extra plot. I want to add another step response. So I'm going to come here to the plot, and I'm going to say a new step. And what I want to look at now is, during all of this analysis, I want to make sure that the control signal or the input to the plant doesn't exceed large, ridiculous values. So what I actually want here is I want the step response from R to U here. So again, all you got to do is click on this drop down and look for, here we go, R2U. This should be the plot now showing, in order to get this step response, here's the control authority that's needed, or the control signal that's needed. And you can see this is getting a little complicated, so let me move this over here. I'll put all the step responses maybe together. There we go. So I can look at both the input to output as well as input to control signal. Okay, so now I think we're ready to go. Let's start thinking about adding design requirements. So the first thing we're going to want to do, and the one that I think is probably the most helpful, is let's start thinking about those performance metrics like percent overshoot and things like that. So if you come here to your step response plot, if you just right click anywhere, and you can now come down here to say design requirements, new. So I want to enforce, you get this nice little dialog that comes up. I want to enforce that I want a rise time of 1 second or better. I want a settling time of 3 seconds, and I want less than 40% overshoot. Great. And now if I go ahead and hit OK, this is really cool because you see, I don't know if it's going to show up too well, but there are now white and yellow sections. So the yellow sections are inadmissible, the white are admissible. This is where we want the system to be in. So this looks actually great. It looks like we're actually well, actually, we should take a look here. Yeah, this looks like it's satisfying the system right now. One other thing that we may want to do is, you see, I would like to see the actual percent overshoot and the actual rise time and all of that stuff as well, not just which regions are allowed or not. So what I can do is I can, again, right-click on the white space, and I'll come here to Characteristics, and I'm going to click on Peak Response, and we get a little dot here, and if you click on the dot, it talks about here's your percent overshoot. Great, so we're sitting at a little more than 30% overshoot. We could also continue this pattern, and I can come here to Characteristics. I could look at settling time, and I guess if I move this out, you can see the other dot, and let's do rise time as well. So this is great. We've decorated our plot now, and we now can see, given the controller that we have right now, which is a controller of value 1, these are the performance metrics that we're getting. So this looks great. Let's continue. Coming up here to the root locus, maybe what we should do is let's also add those requirements to the root locus. So if I come here and right click on the root locus now, I can also come here to say design requirements new, and we'll do the exact same thing. So I want a settling time of less than 3 seconds. And you get the white regions and yellow regions. I also want, oops, there we go, design requirement new. I want a percent overshoot of less than 40%. And we should see those diagonal lines. Yep, the diagonal lines pop up. And then finally, we should be able to say design requirements new. And actually, there isn't remember, there's not a mapping of rise time to pole locations, so that's not available, but if you want any of these other things, you're free to add them. Okay, so let's see, where else do we need to add some requirements? So you can see already we got gain and phase margin already being directly read off, so we can see those. Now, down here in the closed loop Bode plot, we need to make sure that we are meeting the bandwidth requirement. And if you remember from our lecture on bandwidth, we're basically wanting to make sure that the frequency at which the amplitude decreases by 3 dBs from the DC gain is greater than 5. So we see here that the DC gain is 0. Let me just zoom in just to convince yourself of that, right? So this looks great. The DC gain is 0. So really what I'm looking for on this Bode plot of the closed loop system is where does it cross -3 decibels? So what I can do is let me deselect the zoom tool. And again, if you right click now, when you have no other tool selected, just right click on the Bode plot. And same thing, we're going to come here to design requirements new. And what I'm going to say is I want the system to be, I want it to be above a specific bound. And you can see right here, you can define what this bound is. We can talk about at what frequency do I need what specific magnitude. So I need this thing to be -3 decibels, and I'm going to draw a line from -3 decibels, going from 1 radian per second up to 10 radians per second, which is perfect because the critical one that I'm looking for is 5 radians per second. It's in this range. So if I hit OK, you see we get this other yellow region, and if I zoom in, maybe it would be a little bit helpful because, again, with the bandwidth requirement, I'm just looking at 5 radians per second. So I'm going to zoom into here. Okay, so this looks fairly great, actually. And interestingly, it looks like we're almost satisfying the design requirements right away. Let me look here at one more thing. Remember we had the step response R to U? So here we go. This is the other one we can look at. So we could see that, yeah, it's only taking 1 volt to achieve this design. So let's actually take a closer look at the root locus. So this is the root locus for the closed loop system. And you remember, this is our DC motor, which has mechanical dynamics, which are a little bit slower, right, nearer to crossing the imaginary axis, and electrical dynamics, which happen very, very fast here. So you can see here there's this pole out at minus 1,000. So most of the action is happening near the origin. So I want to zoom in on that. So if you click on the root locus, so I'm going to just click here on the root locus, and you see as soon as you do that, you get this extra tab up here, which says root locus editor. So if I click here, there's all these tools to help me manipulate the root locus. So I'm going to click on the zoom tool, and let's zoom in to where all the action is happening. So here we go. This looks a little bit more interesting, right? So what we see is the magenta items in the root locus are parameters of your controller that you're able to change. So notice that there are, it might be a little bit hard to see, but there are blue items, like here's a blue X and another blue X over here. Those are poles of the plant which we're not able to manipulate. But since we can change the controller, we move the poles of the plant to closed loop locations, which are these magenta squares. And the magic of the control system designer is that it's going to allow us to change the controller in real time and then watch how all of the different results change in response to that modification. So let me pull up the step response so we can see what this looks like. And I will come back to the root locus editor, and I need to click on it again to get my tab to show up. Whoops, sorry, I had the zoom tool selected, so it actually moved on me. Let me grab a couple of these tools and reposition the root locus where I'd like it. And now, what I'm going to do is I want to click on this little arrow tool. And now, if you come back to the root locus with your arrow tool and hover over any of these magenta items, it could be poles, which are these magenta squares. Later on, we're going to see that you can add zeros or other types of objects, like complex poles or zeros to your compensator, and you can also move those. But what I'm trying to get at is anything magenta is something you can grab and drag and manipulate. So I'm going to sit here, click on the pole, and here's the magic. I can just drag these poles to any other new location on the root locus. So for example, if I want to increase the gain, I can push them up, and look at this. Here's the magic. Notice how everything else changes in response to this modification. So my step response is changing, all my Bode plots are changing, etc., etc. So here's a design, and you might notice this is maybe a design you'd like to consider. We see that it doesn't quite satisfy what I'm looking for. So maybe tell you what, let's back off a little bit. Let's bring the poles down, and again, I'm looking at the I'm looking at the step response to understand what are the performance metrics, because I don't have a second order system. I have a third order system, although it's second order dominant. So you're seeing that these basically these two poles are what matter. We're going to look at a situation later where that's not the case. So again, I just want to bring your attention that you really should be staring at the step response. Kind of ignore all the white and yellow regions in the root locus. They don't matter quite as much. But here we go. Let's say this is a design I'd like to consider, right? And we can come over to this side of the control system designer, click on C, and we see that here, a gain of K is equal to 1.3862 will yield all of this behavior. Let me show you a real neat feature of the Control System Designer. The whole point of the Control System Designer is to allow you to rapidly iterate on control designs to try to find one which meets your needs. So if you come here to Control System Designer, what you may want to do is periodically store or remember different controller designs. So for example, maybe I really like this controller of K is equal to 1.38. Instead of me having to whip out a piece of paper and write that number down and try to remember what all the performance metrics associated with it were, you can just come up to this button that says store, And if I click on store, watch this little thing, this window that says designs. If I click on store, I get this thing that's called design 1. Design 1 is this controller. So now let's say I want to move these poles and try a different design. Maybe I don't like how much overshoot there is. Let's pull this down a little bit more. Keep going. I don't know. Maybe, whoops. Let's go. How about all the way down to the real axis? Here we go. Okay, so this is another design that I maybe would like to consider. So again, I will just hit store, and now I get design number 2. And what I can quickly do is now flip between design 1 or design 2. So for example, I can go ahead and say, all right, actually I don't really like design number 2 that I'm sitting at right now, because I noticed, oh, look at this, we don't meet the rise time requirement, right? It takes us too long to rise. So I really want to go back to design number 1. So I'll just click on retrieve design number 1. And wha-bam, we're back to where we were earlier. This is actually even cooler. You could even compare multiple designs. Let's get a third design. How about somewhere in between those two, design 1 and design 2? I'll make a happy middle ground. How about something like, oops, I want a K of 0.55-ish, just because, okay, this is pretty close. K of 0.55-ish. And look, this seems also reasonable, so let's go ahead and store this. So now what if I want to compare all these designs? Well, just go and click on this compare button, and maybe I will compare, we can do all three if we really want to. And look at this. This is really awesome, because it will now overlay all of those different designs in all of the different plots, and you can understand how they have advantages or disadvantages over one or the other. So in this case, what I want to look at is, let's clear all of, oh, sorry, I somehow didn't clear, I missed clicking on design number 3, because that's the one I actually want. So tell you what, let's clear all of our compares, and let me go ahead and retrieve design number 3. Okay, so design number 3, here we are. This is the K of 0.55, and let's go ahead and double check that this matches and meets all of our design requirements. So coming here to the step response between the reference and the output, we see that yes, the rise time is better than 1 second, the percent overshoot is less than 40%, and the settling time is less than 3 seconds. That looks awesome. Let's also, while we're here in the step response, double check the control signal. So this is great. It only uses a little more than a half volt in order to achieve this type of performance. Let's come here to the Bode plot of the loop transfer function. So we see, yeah, we've got more than 20 decibels of gain margin, and we have more than 30 degrees of phase margin, so that satisfies. And finally, let's check our bandwidth requirements. So here, we need a bandwidth of 5 radians per second or better, so I need to check where does this thing cross our -3 dB line. So this is a little bit harder to read. I think here's 1 radian per second, and this is logarithmic, so here's 2, 3, 4, 5, 6, so somewhere between 6 and 7. So I would guess the bandwidth of this is, about 6.5 radians per second. So great. This design looks awesome. Design 3 looks like the one we want to go with because it meets all of the aforementioned requirements. So we should maybe think about moving on to the next step, right? Is step 5 is, I like this this controller. Let's make sure we save it so we don't lose it. Okay, so now that we've completed step number 4, which was designing the controller, which we saw was basically grabbing and dragging magenta items in the root locus to meet your requirements, we can start thinking about trying to save our controller that we've designed. So the next step, step 5, is I need to export the controller out of the control system designer and into the MATLAB workspace. So what I mean by that is, if you come back over here to the control system designer, notice there's all these things that we've made. We actually made the C. That's actually what we design here in the control system designer. That's our controller. Now, if you come back to MATLAB, you'll notice it doesn't exist over here in the MATLAB workspace. So I can't go ahead and say save my controller.mat C, right? Because there's no variable C here. All of these variables right now only exist in the control system designer. So what I need to do is I need to get those back out to MATLAB. So in order to do that, I'm just going to come over here to the export, and if I hit this little drop down, I'm going to say export tune blocks. And when you do that, you get this little window which allows you to export whatever you'd like, all of these different things. Well, the only thing I really care about is the Model C in the Control System Designer, which was my controller. And we can change what I want to call this. We can call this maybe, let's call it proportional controller. And if I now hit export and come back to MATLAB, you see that it has made this thing called proportional controller. So if I look at this, here it is. I've got this now exported to the MATLAB workspace. This is the controller that I want to use. Okay, so now let's go ahead and move on to step 5. Or excuse me, step 6. Now that we've exported the controller, we can go ahead and save it, both the controller and the session. This is what the workflow I usually like to follow. So what I mean by that is let's come over to MATLAB, and now we can go ahead and save, whoops, here, and I guess we didn't call it C, we called it proportional controller. So it's really this simple. All I'm going to do is just save this ZPK object into a file. And when I do that, here it is. Here's mycontroller.mat. So I've saved the variable. But all of this work that we did back in the Control System Designer, right, moving all the poles around, setting up all these plots, this was a fair bit of work. You might want to save that as well. So what I mean is you can come up here and click on Save Session, and what that will end up doing is it will create a mat file, which should hopefully be loadable in the future. So let me go ahead and call this Control System Designer Session. Maybe let's call this _ proportional controller .mat, and it will just save that in the current directory. So let me just illustrate that for you. Where is my current directory? Here it is. So here's the controller that had only the variable C, and here is our mat file, which contains the Control System Designer session. So a word of warning with this, you might think this saves everything perfectly, but let me go ahead and show you what happens. So let's pretend that we're done for the day. Let's close the Control System Designer, and we want to come back and boot this back up again. So let me go ahead and just clear everything. Maybe that's a good way to do this. Let's start from scratch. So everything is gone. I can go ahead and start my Control System Designer like we did earlier, and bring it up, and here we go. It's loading up our blank Control System Designer. So let's go ahead and open a session that we just saved. If I come here to, here it is. Here's the session we just saved, and if I open this up, give it a second here to load, it will get most of the items correct. It will load in all the objects, but notice here that it really didn't save my layout too well, so you may have to play around with this a little bit to get this exactly back to where you want it to. So for example, I think we had the Bode plot of the loop transfer function was over here. I think we had, actually, yeah, this Bode plot was down here. We had this over here. Oh, come on. And then we had our root locus on top. Okay, now we're getting a little bit closer to where we were. But again, notice you might have to go ahead and add these characteristics back. So it's not a completely foolproof method, but look, it did save a lot of the items. Like, it definitely saved the plant, it saved the controller, and it saved all of our other designs that we had built earlier in case we wanted to go back to one of these other systems, right? Okay, so this is looking great. I think we've done step 6. Okay, so the last step in our workflow is step 7, where we want to simulate this system to validate performance. So what you could easily do is, one option is come over to MATLAB and just start up Simulink and build yourself a blank model that represents this system with the controller and all of the stuff that we had earlier. So I will get a transfer function here and make this GP of S, and then I guess we could come in here and call this GP num and GP den, and then we could go get another gain which represented the controller, which was 0.55, I think was what we had, and you could start hooking this up and building the system, and hitting simulate to make sure that you got the performance that you designed in the control system designer. And this is a perfectly viable way to go, right? You could go ahead and make all of these blocks yourself and hook everything up. But as the systems get more complicated and you want to rapidly iterate, I think you can see why this is a little bit cumbersome of having to build the Simulink model yourself. So what's super awesome about this is, let's go back to the control system designer. And this is the system. Oh, wait, sorry. Actually, no, this is not the system we want. We better go back and retrieve design number 3. This was the system we wanted. Now, with, let me triple check. Yeah, with a K of 0.55. Let me show you a really awesome button that the control system designer has. So if we come here to the export tab, and there's this other thing that says, look at this, create Simulink model. So instead of me grabbing and dragging blocks by myself, if I click on this, it knows what type of architecture we're using. So it knows all of the blocks, it knows the architecture. So if I click on this, I get this little warning here. Maybe we should read this quickly. And what it says is it's going to create this Simulink model, and it's going to export all these things like FCGH to the MATLAB workspace. So you better make sure you don't have any other variables called FCG or H, because it's going to overwrite them. I know I don't, so I'm just going to go ahead and hit continue and yes. And if you give this a second, what it's going to do is basically auto-gen. Here it is. It popped up on another window. I'll drag it over here. Look at this. This is amazing, right? It automatically generated the appropriate architecture. Let me just compare this. Maybe I'll pull this up on one side and pull the Simulink model up on the other side. Notice it did almost perfect. I want to say almost perfect, because the one thing you might want to notice here, and I feel like I should call out, is that the input block here, if you double click on this, for some reason, whatever, it decides to use a sine wave as an input. I like to look at the step response, so I'm going to make a very, very minor modification to this auto-generated system and basically input a step instead. So I'm going to get a step function, and I'm going to make it go at how about 2 seconds. Let's go, unit step value, and let's put in a manual switch just so I can quickly change between these two different inputs, and connect this up. Here we go. Flip the switch to down, and let's also maybe put an additional scope on the control signal, because that's always something that's interesting to notice, to see how much control authority are you actually exerting. So if I go ahead and hit run, this Simulink model ran, and I can look at the output. Let me pull this up. Here we go. And I can look at the control authority. Here we go. Here are the two. And these look exactly like what was predicted in the control system designer. Let me see if we can pull all these up maybe side by side. Let me pull this to come on. There we go. Okay, so we got the step response of the actual output and the control authority. So let's line these two up, and look at this. They look perfect, right? Great. So with that, I hope you've seen how the Control System Designer is a really powerful tool to help us design and iterate on linear controllers. Of course, in this case, we used it to synthesize a very, very simple controller, just a proportional controller, but this sets the stage, and I wanted to just show how this tool can be used, because in our future video, we're actually going to be talking about how to design PI or PI pseudo-D controllers using this workflow. So, for those of you who have been with us a while, thanks for watching, and if you're new to the channel, please subscribe, and let me know what you think in the comments below. I hope to catch you at one of our future videos where we're going to look at applying this Control System Designer to more complicated systems. So, until then, I'll catch you next time. Bye.